Hi guys, you're watching another episode of Pragmatic Software Engineering. I'm your host, Ben. Today in our data structures model, we will be discussing a way to score our algorithms and data structures. Recall that we don't have infinite resources. You may have 4 cores in your CPU and 8 gigs of memory, but that's not the case for everybody. In reality, there's thousands and maybe even millions of computers out there that have different specs. Because computers have a myriad of different specs, we cannot score our algorithms by time, but really by instructions, and also by the amount of memory used. Specifically, we model the runtime complexity in terms of the size of our inputs. When we score our algorithms and our data structure, we do it in terms of O of n. And O of n describes the worst case runtime scenario for the input n. In this video, we will be discussing runtime complexity and stack size complexity. Let's start with iterating over an array. Given an array full of random integers of some arbitrary length, we want to figure out what is the greatest integer in that array. Think about this. How many elements must we go through to deduce the maximum value of the array? Well, we had to visit all of them. So worst case scenario, we have to go through every element in that array. Our score for this algorithm is O of n. However, since we didn't do anything with recursion and we didn't mess around with any stacks, we can conclude that our stack size or stack space complexity is constant. A for loop generally denotes a relationship of O of n, and when you have nested for loops, you multiply your O of n by n. So a nested for loop would yield a runtime complexity of n squared. But if you have a for loop to do some instruction, and then you have a for loop after it, it's really 2n. If you write a for loop inside of a for loop, you are multiplying your complexity. So in the example, you're displaying an n by m grid, which means where n is the row and m is the column, you will have to for loop over every row and for loop over every column and display a grid. Therefore, your runtime complexity would be O of n times m. When we are scoring algorithms, we don't care about these coefficients. We always drop the coefficient. So even though you may have a runtime of 2n, you will say that your runtime is n. When using recursion, it's common to see both a non-constant runtime complexity and a non-constant stack complexity. Let's return to the example we did a couple of episodes ago where we talked about computing the factorial of a number using a recursive approach. Let's use the example 6 factorial. When we start from 6 factorial, we have one thing on the stack, that is 6. Then we allocate a new layer to the stack for 5, and we allocate a new layer for the stack at 4 and 3 and 2 and 1. Our space complexity is equal to the number that is put in as the input. Although we're using the stack to organize our data, we still have to do computations on this data. So if you think about it, 6, 5, 4, 3, 2, 1. Then we can return our output. We still had to visit every number from 6 to 1. It's linear. If we go to the number 7, we have to go from 7 to 1. If we go to 1000, well, we have to go from 1000 to 1. The relationship between the size of the input and the amount of instructions we have to run is linear. Therefore, our O of n, our scoring criteria for this recursive factorial algorithm, is O of n. And that's it. That's how recursion works. It may be a little bit clumsy as you begin to practice it, but as you practice it more and more, it'll become very intuitive. I hope you enjoyed this video. As you can see, I try to put a lot more effort into the effects and the recording of it. Let me know what you think. Please like and subscribe. If we were really helpful, show us to your friends. If you have any questions, please go to pragmaticsoftwareengineering.com. Thank you very much.